To introduce game theory and strategic thinking, I want to talk about a very big game, the stock market, and a game that we can use to model how people make stock market decisions. The game is often called the Keynesian beauty contest, based on some remarks made by John Maynard Keynes in his great book, The General Theory of Employment, Interest, and Money. A stock's value is determined by what others are willing to pay for it and sell it for, and nothing else. This, in fact, is like pretty much everything else on the market. So to estimate the value of a stock now, we need to estimate what others will pay for the stock in the future, knowing at the same time that they are estimating its value based on what we will pay for it in the future. So this is illustrated in this rather sinister meme. The market is nothing but a guessing game where you try to guess what others will guess. So Keynes likened this to a special kind of beauty contest. Here's a passage from his book. Professional investment may be likened to those newspaper competitions in which the competitors have to pick out the 6 prettiest faces from 100 photographs, the prize being awarded to the competitor whose choice most nearly corresponds to the average preferences of the competitors as a whole. So you're not trying to guess which face is the nicest, rather you're trying to guess which face will other people choose. And of course they're not trying to guess which face is the nicest either, rather they're trying to guess which face will other people think that other people think are the nicest. So that each competitor has to pick not those faces which he finds himself finds prettiest, but those which he thinks likeliest to catch the fancy of the other competitors, all of whom are looking at the problem from the same point of view. Well, in this last passage, it's very important, right, that people are looking at others and they're saying, what are they going to think? Knowing that they are looking at them, thinking, what are they going to think? So games using the thinking underlying Keynes' analysis have been studied quite widely by economists. And they use the term beauty contest game to describe these games, but sometimes you'll also see beauty contest or guess a number game. And all of those are essentially the same thing. So this is the kind of task people are doing in the experiments. They are asked to provide an integer between, say, 1 and 100, between some range. The number closest to 2/3 of the average number will be the winner. Okay. For example, if the average number is 90, then a guess of 60 will win. It's unlikely that 90 would be the average number, but should it be that, then 60 would win. And perhaps the pioneering work on this is done by Rosemary Nagel in this classic paper published in the American Economic Review. So imagine you were playing this game with 1,000 randomly chosen people. Write down your estimate of 2/3 of the average guess. Just take a few moments to think about what might happen. Think about the other people involved, what they're likely to do, and then write down your estimate of 2/3 of the average guess. Okay. So how can you solve the game? Well, this is some basic terminology from game theory to think about. First, you have 100 strategies available to you. These are the numbers you can choose. And let's assume that all the guessers are rational, including you. That's a basic game theoretic assumption. That means you assume that everyone knows that everyone is rational, and everyone knows that everyone is rational, and everyone knows that everyone knows that everyone knows that everyone is rational, and so on. This is called common knowledge of rationality. This is kind of assumption of perfect rationality, including rationality about the other person's rationality. So here's a way to solve the game. Think about it. First, choose a strategy at random. Let's say it's 45, and let's assume everyone chooses that strategy. Then compute your best response to that strategy. Well, since it's 2/3 of the average, if everyone chooses 45, then your best response is going to be 30. Next, assume everyone thinks the way you do in step 2. Compute their response to your strategy. Well, 2/3 of 30 is 20, so that's going to be your best response. And then compute your best response to their new strategy. And that's going to be 13 or 14. And you continue doing that, right? Because remember, you're assuming that everyone is rational and they're assuming you're rational. So all of these stages, you're assuming that everyone will go through. And then you end when the adjustment process leads to an unchanging strategy on both sides. So when you reach a point where you're saying, look, if this number is chosen, they're not going to change their mind. And similarly, if that number is chosen, I'm not going to change my mind. So we're going to be kind of stuck there. That's like an equilibrium point. It's called an equilibrium. Then that's when it ends. Okay, and it ends at the number 1. Okay. Will everyone choose 1? Okay, so that's what rational people will do. But will everyone choose 1? Probably not. Okay, if everyone is fully rational and assumes everyone else is fully rational, they will. 1 is the Nash equilibrium. Okay, and the reasoning we use to get to 1 is called successive elimination of dominated strategies. Okay, this is John Nash, by the way, who first described the Nash equilibrium as part of his PhD thesis. But now, suppose not everyone is rational. I've already suggested they probably aren't. And what's going to happen? Well, then the winning number will be more than 1. That's the smallest number it can be, so any deviations have to be higher. So can we do better than just simply saying, oh, the winning number is likely to be more than 1? Can we actually estimate what that winning number is likely to be? So here's a possible way to think about what might happen. Everyone else takes only one step of analysis. Remember, we went through a whole series of steps of analysis. We said, okay, imagine it's 45. Then if 45 was what everyone was saying, that everyone in fact would choose 30. And then if they thought everyone might take 30, then of course they would take 20, and everyone's going through this process. But suppose people only take one step. Okay? Now everyone also is not completely out of it. They all know the answer can't be higher than 50. The average isn't going to be more than 50. So they start with a random number between 1 and 50 and say, well, that's, the average is going to be somewhere in that range. And that average is about 25. And then they say, well, if the average is, whatever number I have chosen, I'll take 2/3 of that. Well, since 2/3 of 25 is about 17, that's going to be their estimate. Okay. So they're taking 2/3 of the average that they thought of, and 2/3 of those averages is going to be 17. Okay. Let's call this level 1 thinking. Now suppose you went one step further, right? You would say, well, everyone is going to do one level of thinking. I'm going to go 2 levels of thinking. You're going to go one step forward. It's going to be a number like around 11 or 12. Okay. Call that level 2 thinking. And it turns out that in problems like this, if you go through this level of thinking, you will probably not go far wrong. Okay. Now you might want to adjust upward a bit, because it's possible some people will go higher than 50, and typically there will be a few, people who don't really understand the task maybe. If you have a very sophisticated audience or group, they might be lower than 50, or sorry, lower than 11 or 12. And whereas some people might give lower numbers, they're going to have a smaller effect on the mean than numbers that go higher. So generally, if you're going to shift, you might want to shift a little bit upwards. Okay? So guess somewhere between 11 and 17, maybe 13. So let's look at some real data from an experiment. Now, Richard Thaler, the Nobel Prize-winning behavioral economist, in his book Misbehaving, he describes a study that was done with Financial Times readers. And what he did is he asked them to guess a number between 0 and 100 and offered a prize to those people who gave a number that was 2/3 of the average. So it was essentially the same task I've just described. What this picture shows is the distribution of answers to the questions, to this question. And you can see there's quite a big distribution here. And I want to go through the kind of reasoning that Thaler suggests, and indeed many others have suggested that people do when answering these questions. And this kind of reasoning comes up with a number essentially the same as the one I suggested, but suggests as well a little more complexity to how people reason. Okay, so this is the whole distribution here. Now, let's start. The winner came up with a 13, which is probably what you would come up with if you followed my advice. But notice that there are some substantial peaks here, some interesting peaks. One of the peaks is at the number 33. What's going on here? Well, Rosemary Nagel used the term first-level thinkers to describe these people. So what she says is that what people do is they think that 50 might be the average, because that's the average between 0 and 100. And then what they do is they compute 2/3 of that average, and they give that answer. Okay? So it's a kind of, quite crude, approximation to what people might do, and that's their answer, right? And then some people say, well, if the average is, if some people are thinking the average might be 50, then they're going to give 33 as an average. And if they give 33, then 2/3 of that average is going to be 22. And indeed, you get quite a substantial number of people. That's the majority of people who give the number 22. And you also get some people who, as Thaler says, have too much economics training, meaning that they work out the Nash equilibrium of the game as if everyone's rational, but what they don't realize is that people are not really as rational as all that, and they're not going to go to give this perfect answer. And so consequently the winner is 13. Now the winner is 13, which is just approximately 2/3 of 22, with some people pulling them down a little bit, and some people, like these at the end here, pulling it up a little bit. So it's well worth reading Thaler's book, Misbehaving, to learn a bit more about how people think about these kind of problems. Here's some other interesting statistics in this kind of research. What this shows is that how people's choices change over time. And what that means is a number of trials that they in which they play this game. So if you look here at the 2/3 of the average line, what this shows is, well, what's the average number people get in one experiment, right? In which they're asked to give 2/3 of the average for just one trial. What happens after 2? So the second time they do it, the third time, and the fourth time. And this audience was clearly not super sophisticated, because they started out giving an answer of 40, right? But what you can see is that with time, they get better and better at it, in the sense that they get closer and closer to the Nash equilibrium. And you can kind of imagine why this might be the case. You start out by saying, oh, I think the average is going to be 40. So everyone gives, some number around 40. And then when the correct answer comes, and it turns out to be 2/3 of 40, about 27, so they say, oh, it was 27 last time. So this time everyone's going to say, so 27 was the right answer. So now everyone gives 27, but this time it's 2/3 of that 27. That's the correct answer. So next time it's around 2/3 of 27 that people give, and they keep doing that, and eventually they get driven down to the Nash equilibrium. Similarly, and this is an interesting case here, in the 4/3 of an average game, you can work this out for yourself, the Nash equilibrium is 100, right? And you can see that people start out too low and then they zoom up towards 100, and this happens over a number of studies. So I'd also like you to think about this game here, the 2-person beauty contest game, and this is something you can kind of try with your friends. Okay? I just want you to try solving it. So 2 people play this game, and each tries to guess 2/3 of the average number of their 2 guesses. What will the answer to this game be? It can be any number, positive or negative, that people give. Okay, so it doesn't have to be between 1 and 100 or 0. There's no range in particular. Just ask people to give. Each person guesses a number, and the answer is going to be 2/3 of the average. And what is the best guess? The guess that's closest to the actual value. I'll let you work it out for yourself. Okay? As I put here, you can put bounds on it if you want.